has been more than 4 centuries since human eyes first gazed at the heavens through a telescope. Since then, the telescope has transformed our understanding so deeply. It is almost as though the universe itself has changed before our eyes. Wandering planets, once no more than bright lights in the sky, have become entire worlds, each with its own unique features. Faint patches of light have morphed into spectacular nebulas, where new solar systems are born by the thousands. Or giant galaxies gracefully flying through the cosmos, millions of light years in the distance. The universe itself has proved to be far larger and more ancient than our ancestors ever imagined. In this century, 2 questions have set the course for our telescopic exploration of the universe. The first is about the origins of the universe itself. How did all of this get here? And what are the conditions that allowed the universe to evolve from an initial explosive event, known as the Big Bang, into its present form, with stars, galaxies, black holes, dark matter, and more. The second question has to do with our own origins, and whether the conditions that led to our emergence here on Earth are common enough elsewhere in space to allow us to find other worlds harboring civilizations like our own. The tools that will allow astronomers to get at these questions are nothing short of extraordinary. They are telescopes, but telescopes larger and more penetrating than any ever built. Some will be built on Earth, others will orbit in space. Together, they will allow us to see farther than humans have ever seen before. To understand how, consider the Hubble Space Telescope, currently astronomers' state-of-the-art instrument for exploring the universe. The Hubble is really a sophisticated light catcher. It uses its giant primary mirror to grab as much light as it can from distant objects and then focuses that light to produce an image. Looking far beyond the stars of our own galaxy, Hubble's big mirror catches enough light to see very faint galaxies billions of light years away. But galaxies quickly become fainter and are invisible to Hubble beyond this point. So to see more and see farther, astronomers are developing the James Webb Space Telescope. This is a light catcher par excellence, with a primary mirror that covers 6 times the surface area of Hubble's. Any telescope that big is certain to take astronomy to a new level. But getting such a giant into orbit is no small feat. For starters, it's already too big for any rocket to carry. That's why, Instead of a single primary mirror like Hubble, the James Webb Space Telescope will use 18 smaller, precisely aligned mirrors that will connect together like a honeycomb after the telescope is launched. These smaller mirrors are also easier to produce and lighter to carry into space. But size alone is not enough. Even with a big mirror like this, the universe makes the most distant galaxies nearly impossible to see. This is because the expansion of the universe pulls the galaxies away from us and shifts their light toward the red end of the spectrum. The very farthest galaxies have been shifted so much they shine not in visible light, but in the infrared. So, to have a hope of seeing even further than Hubble, the James Webb Space Telescope will be tuned to see the heavens in infrared light. This is perfect for observing the distant universe. And it has to be perfect. Because unlike the Hubble, which is much closer to Earth, the James Webb Space Telescope will be too far away for astronauts to reach. That means the telescope will have to work all on its own, with no hope of repair if something goes wrong. Technicians are carefully assembling the telescope. When it's ready, it will be folded up like an elaborate umbrella and launched into space. After a month-long journey, the telescope will unfurl. Slowly and methodically, the various components will unpack themselves. The sunshade will unroll, and the solar panels, much larger than Hubble's, to compensate for a more distant and weaker sun, will deploy. Finally, the gold-coated segments of the mirror array will open like the petals of a flower and click into place, ready to direct light into the telescope's detectors. All that will be left to do then is to look and let the universe reveal itself. The launch of this ambitious telescope will be a major achievement, but it will only herald the start of a new era. To see where that era will lead us next, our quest for bigger and even better telescopes will bring us back down to Earth. Perched on lonely mountaintops in distant corners of the globe, the world's great astronomical observatories seem to exist between two realities: the terrestrial and the celestial. The largest observatories are finely honed operations, more like astronomy factories than lonely outposts. They use sophisticated optical techniques to help cancel out the effects of Earth's atmosphere. As a result, the biggest telescopes on Earth have come to complement and rival the Hubble telescope in space. But now astronomers have come to the limits of what the largest observatories on Earth can see. To see the birth of the galaxies, and to look for planets forming around other stars, the next generation of telescopes must be larger. Far larger than anything ever built. Today, 3 projects are leading the way, setting the stage for the next wave of great observatories. Each has its own unique design and location, but all will be built to address the same underlying need: collecting as much light from the distant universe as possible. This is a technical challenge of the highest order. For the giant Magellan telescope, the answer is to combine 7 of the largest mirrors possible and hold them together so they can operate as one single super mirror, 24.5 meters across. Like an alien flower, the giant Magellan telescope will turn its petals skyward to gather starlight from the summit of Las Campanas, a spectacular mountain location in Chile. The estimated cost is $700 million. Pushing the limits even farther, a consortium of nations is planning the TMT, the 30-meter telescope. At a cost of $1 billion, it will be built on Mauna Kea and dwarf the other large telescopes that already crowd Hawaii's tallest mountain. Unlike the giant Magellan telescope, the TMT will not consist of a few large mirrors working together. Instead, following from the design of the nearby Keck telescope, it will view the heavens with a mosaic of 492 mirror segments, each just over a meter across. So equipped, TMT will be able to pursue its key goal of investigating the early universe. From the birth of the first stars to the formation of the galaxies. An even larger telescope is now being planned by the European Southern Observatory in Chile. It's called the EELT, short for European Extremely Large Telescope. Like TMT, it will also use a segmented mirror, but in this case made up of nearly 1,000 individual segments, all fitting together to create a light-gathering surface that is a whopping 42 meters across. At an estimated cost of $1.4 billion, this would be, by far, the largest telescope ever constructed. It will be located on Cerro Armazones, one of the most promising locations in Chile, and perhaps the best mountain in the world that does not yet have a major observatory on it. But the EELT will far exceed previous telescopes in its ability to see the early universe. Its instruments will also specialize in identifying the signatures of different chemical elements, helping to identify the ingredients from which the first stars and galaxies were made. As well as look for signs of molecules important for life in the atmospheres of planets around other stars. All three of the new giant telescopes could be in operation by 2020, though this will depend on funding. Plan is they will work together with and follow up on discoveries made by the James Webb Space Telescope. They will also be engineering and scientific marvels, monuments to our innate desire to learn about the universe around us. But above all, they will be doorways to future understanding. The tools that will help us discern hidden clues to the nature of the universe and the riddle of life, and point the way forward into the infinite unknown. The next generation of telescopes, both on Earth and in space, promise to help answer two of the most important questions we have ever asked about the universe. Where did all of this come from? And are we alone? These questions are not new. What is new are two surprising finds that suggest exciting answers may lie just out of the reach of current technology. These findings are now helping fuel the push for new instruments of astonishing size and ambition. The first surprise is the discovery of dark energy, a term that astronomers have coined for something they barely understand. Simply put, dark energy is a property of space itself. It seems to exist everywhere, and yet cannot be measured directly anywhere. It was discovered by looking at a type of supernova, a brilliant explosion that is triggered when a massive star starts pouring vast quantities of hot gas onto a small, dense companion known as a white dwarf. Once the burden on the white dwarf reaches a critical limit, it becomes unstable and suddenly erupts, generating enough light to outshine an entire galaxy. Then, by comparing both the motions and the distances of many supernovas, astronomers can see if the expansion of the universe has changed over time. When researchers first started doing this in the 1990s, they made an astounding discovery. The expansion of the universe is speeding up. That means most of the galaxies we observe are moving away from us and from each other faster and faster as time goes on. Something is causing this to happen, and that something is dark energy. One new telescope is ideally configured to probe this mystery. It's called the Large Synoptic Survey Telescope, or LSST. While it's not as large as some of the other future telescopes currently on the drawing board, the LSST will have the largest field of view of any telescope its size. Specially designed for a wide-angle perspective, it will take in vast swaths of the heavens all at once, managing to image the entire sky twice every week. All of this data will allow astronomers to look for and measure the effects of dark energy in multiple ways. Those measurements will help distinguish between different theories for what dark energy is and how it works. Theories that can eventually be tested by the much larger telescopes to come. The other question motivating the development of new telescopes is one that goes to the very heart of our existence. We know, because we are here, that life is possible. What we don't know is how likely life might be, and whether the odds favor us eventually making contact with other civilizations on distant worlds. One way to address that question is to find other places in the galaxy where life could be. That's why the discovery in the 1990s of planets orbiting nearby stars electrified astronomy and captured the public's imagination. So far, none of these planets share exactly the characteristics of Earth, including size, composition, and temperature. But NASA's Kepler spacecraft, currently in orbit, is capable of detecting other Earths, and when it does, larger telescopes will be needed to follow up. Astronomers are now considering how best to create a new kind of orbiting space telescope that will be able to zoom in on the other Earths that Kepler finds. To succeed, such a telescope will likely be both large and complex. Its job will be to tease out the faint light of an Earth-like planet from the billion times brighter light of the star it orbits. If it succeeds, that light can then be analyzed for signs that there are biologically important molecules in the planet's atmosphere, like oxygen or water. Just a generation ago, astronomers would have thought such a feat virtually impossible, but it may only be a decade or two away. In the end, it is our curiosity about ourselves and our desire to find others like us that will drive the development of telescopes to even greater heights. With the telescopes of the future extending our vision even farther into the cosmos, it seems there is no end to what we may see.